Hello, dear viewers. Welcome to the second video of my channel. And to start off, what if I tell you that everything that exists in our universe as of now and that we know about, the stars, the black holes, galaxies, etc., all of them are one chapter of an entire book of the universe, the history of it, or you could say the timeline of our universe. And in this video, we are exactly going to be talking about that from the Big Bang, the beginning of time itself as we know it, to the fate of it again as we know it. Now, to start things off, you see, first of all, we have this scientist, Edwin Hubble. You see, what Edwin Hubble did was that he discovered that our universe is in fact expanding. Now, how did he do that? You see, to understand that, we must first understand the Doppler effect. Now, most of us have probably studied about the Doppler effect, but what happens is that if you have, say, a car that is coming towards you while their horn is on, right? Now, while they are pressing their horn and they're coming closer towards us, the frequency of it will eventually get higher and higher as the wave gets squished more. So the wavelength will decrease and the frequency will increase. Now, in that case, we will hear a louder sound as the car is coming towards us, and the sound will be more pitched because because its frequency is more. Now, as the sound is going away, the wavelength is stretched, and the things happen completely opposite to as they happen when the car is coming towards us. Now, similar to sound, light does the same thing. So, if I have an object that emits light, and I have a detector. Now, if this object is going away from the detector, the light wave will be stretched as the object is going away, and thus the wavelength will increase. Now, because the wavelength is increasing, it will lean towards the red side of the spectrum, and that is why it appears to be red in color, and that is why it is called redshift. Now, if I do the opposite, if the light emitting source is coming closer to my detector, then the wavelength will decrease as it's coming closer, and thus the things will go towards the bluer side of the spectrum, and thus it is called a blue shift. Now, what Edwin Hubble observed is that the farther away the galaxies are, the more red shifted their light is. Now, the only way that is possible is that the space between us and the galaxies are increasing. So if the galaxy is farther away, the space has increased more in size, has expanded more in size, and thus the light gets more stretched, and thus it's more redshifted. And thus this proved that our universe is expanding, which was a big breakthrough in understanding. It actually broke the classical idea that our universe is static, as everybody believed. Edwin Hubble showed it's in fact expanding. Now, there were some implications of this. You see, there came the scientist Georges Lemaitre. Now, what Georges Lemaitre did was that he theorized initially, and after him, many other scientists even proved that if everything is expanding right now and we reverse time in backwards order, we'll see that everything that exists in our universe right now it's expanding, but in backwards in time it would all be getting squished into one tiny singularity that would be the start of all of it, and that they call the point of the singularity of the Big Bang. And this was the birth of the Big Bang theory, where you had the initial singularity with literally all the matter in a space smaller than literally an atom, infinitely small and infinitely dense. Now that point expanded and that event is called the Big Bang, and after which our universe expanded into our modern day universe, and everything is expanding. Now, this was the birth of the Big Bang theory. Now, you see, after that, I want to talk about one big misconception that many people have. It is that they imagine Big Bang as a dynamite exploding and all the stars coming out of it, as if they are exploding from a dynamite or something. But the way Big Bang really works is that, you see, you have the fabric of space and time itself, which actually we could talk about the fabric of space and time more in the general theory of relativity. That will be another topic for another video. But for now, you can understand that our space is rather a fabric of space and time. And with Big Bang, when Big Bang happened from the singularity, the that singularity did not explode as in we would imagine it. It rather, the fabric of space and time expanded, and eventually that expansion increased in four dimensions, of course, the x, y, z and time dimensions. Now, now that we have understood what Big Bang is, we must now truly understand what happened after it, and different eras that existed with it. Now you see, just after the Big Bang, very shortly after the Big Bang, like 10 to the power minus 43 seconds, we had quantum effects dominating. So all the forces that existed were not were not separate forces. The four fundamental forces, which are gravity, electromagnetism, and the two nuclear forces, strong and weak, all of them were not separate. They were all united and unified into one single super force. And there were quantum effects dominating, and the laws of physics that work today actually broke apart at that point, simply because of the fact that just a few, and by few I mean almost infinitely small amount of time, that is 10 to the power minus 43 seconds, just after the Big Bang. Of course, the amount of density, can you imagine, dear viewers, that all the universe that exists today, all of it all of it has been squished in a point, in a literal point, smaller than you can ever imagine. Can you just imagine the crazy density of that point? Can you just imagine how crazy the effect of such a singularity would be? And modern physical laws literally break apart at that singularity point, and that is why it is something that nobody can truly visualize. That is how dense it was. Now, of course, after the quantum effects dominated, you see, from 10 to the power minus 36 to 10 to the power minus 32 seconds, which is just which is a very, very small amount of time interval just after the Big Bang. In that interval, what happened was that there happened a thing we call inflation, and this theory was called then inflationary Big Bang model. Now, this initially was proposed by Alan Guth, this scientist right here. I'm sorry, my webcam just disappeared. Anyway, so you see this scientist right here. His name is Alan Guth. Now, Alan Guth was the scientist who initially formulated the inflationary Big Bang model. But after that, many other scientists like Andrew Linde and many other scientists worked on it. But what it means is that in this tiny interval of time, our universe expanded quite literally faster than the speed of light. So what happened is, this fabric of space and time right here, this just after the Big Bang, and just after I mean infinitely small amount of time after, you could imagine, because it's so incomprehensible how small that interval is. The fabric of space and time expanded, but just after it, that is 10 to the power minus 36 to power minus 32 seconds, the fabric of space and time expanded faster than the speed of light. Now, many of you must have a doubt that how can the fabric of space and time expand faster than the speed of light? Because Einstein's special theory of relativity shows that nothing can go faster than the speed of light, and it is the speed limit of a universe. But the thing is, the fabric of space and time isn't really an ordinary object that it will follow such laws. If I have a box like this or a book like this, such things are ordinary matter and ordinary energy, and that is why they do follow Einstein's laws. However, the fabric of space and time, you could imagine it as the kind of as in a stage, a arena on which all the different objects are acting. Now, that stage itself is not a separate object unless you observe that stage from an outsider perspective. And the fact is that we as humans, and we don't know whether there is anything outside or observable universe and this fabric of space and time or not. And of course, that is why we cannot look at it from an outsider perspective, and that is why it is not an ordinary object for us, the fabric of space and time. It is the arena on which we are acting on, and it for us it is not a reference point or a point of perspective for us, because it's simply not a separate or ordinary matter and energy as we imagine it. It's rather the arena on which all of us are acting, and because we are not outsider observers, we cannot distinguish we cannot classify it as as a separate object. Now, you see, you must be wondering, how did these scientists right here know that our universe did go through the inflationary period and just after the Big Bang? Now, you see, the reason for this is because of these four problems. Coming to the first one, you see, first is the horizon problem. Now, I want to show you the image of, quite literally, the relic of our universe. Now, this photo right here, this is the cosmic microwave background radiation. Now, this is the photo of our universe just 380,000 years after the Big Bang, and it is the oldest photo of the entire universe that we have. And now we are 13.7 billion years after the Big Bang. Therefore, it is extremely old. It's like an ancient relic of our universe. Now, why it is 380,000 years and not before that? Well, I'll come to that later. But for now, just accept it. I'll come to it later in this video. Now, the scientists were confused why in this cosmic microwave background radiation, the extreme parts of our universe, the left part and the right part, are so spookily similar. You see, our universe follows a thing we call homogeneity. Means wherever you look in our universe, it seems almost the same. And the temperature across our universe is about the same. Now, this is called homogeneity, and our universe is roughly homogeneous. Now, scientists were confused how the extreme left part of our universe and how the extreme right part of our universe can be so similar. And this was essentially called the horizon problem. Now, inflationary theory solved this problem by showing that if just when the Big Bang singularity existed, these extreme right and left parts were all so close that they could reach an approximate thermal equilibrium. And then the fabric of space and time expanded faster than the speed of light. So now, to us, they appear so distant. But back in the day, 13.7 billion years ago, back in the day, I mean by back in the day, they were very close to each other in a singularity, literally a point, and that is why they reached about roughly a thermal equilibrium, and that is why our universe seems so homogeneous. So this is why inflationary Big Bang model solved the horizon problem. Now, secondly, we have the flatness problem. You see, the flatness problem says that if initially in the singularity of Big Bang we had even minuscule curves or minuscule curvatures in our universe, they should seem now, because the universe's space-time fabric has expanded so much, these minuscule curvatures should be so big that they seem to us like different objects and huge peculiar objects existing in our universe. But our universe, as it was observed, is roughly flat. So why do we not observe such huge anomalies in our universe? Well, you see, the inflationary model showed that if just after the Big Bang, the fabric of space and time expanded faster than the speed of light, such tiny curvatures would have been flattened out roughly. And that is why now that we are here in the future, our universe roughly seems flat. And thus the inflationary Big Bang model solved the flatness problem. Then we had the monopole problem. Monopole problem, according to the equations of scientists, during the time of Big Bang, there should be some monopoles and some, you could imagine, exotic particles existing. And after the universe is so big now, such particles should be in abundant quantity. So why they don't exist in such abundant quantity? You see, inflationary model showed that if a universe expanded faster than the speed of light, such monopoles and such exotic particles would be so diluted that they would be almost negligible, and that is why they don't appear to exist a lot in a huge quantity in our universe. And finally, the fourth thing that inflationary model explained was how galaxies formed via quantum fluctuations. Now, I want to show you a photo of something extremely spooky. This is the photo of quantum fluctuations. Just look at this thing. What this is that, you see, in our universe, what is happening is vacuum of our universe isn't truly empty. Vacuum of space-time isn't truly empty. You see, there are a particle and an antiparticle, very small particles coming out in and out of existence. They annihilate each other and go away, and this is happening in our entire universe all the time and everywhere, literally. And these are virtual particles, and the reason why I call them virtual particles is because, you see, these particles are so short lived that one particle comes up and one antiparticle comes up, and they annihilate each other in such a small interval of time that you could imagine it as the universe doesn't even literally forgets about whether these particles existed or not. And this photo of quantum fluctuations isn't really a photo of these particles themselves, because these particles are literally so short lived that you cannot observe them directly. These are like the shadows of these particles, the fluctuations these particles created when they annihilated. Now, these are called quantum fluctuations, and they happen everywhere in our universe, in the vacuum of universe, and that is why it isn't truly empty. And it is occurring because of a mysterious fluctuation happening in different quantum fields that nobody on this planet truly understands, dear viewers. This is literally a phenomena happening everywhere in our big universe, and nobody really understands why they are happening. There are, of course, current speculations that they are happening because of tiny violations of the uncertainty principle and energy conservation laws. You can research about them more, but I'll also talk about quantum fluctuations and many other effects they give rise to, like Casimir effect or black holes Hawking radiation. I'll talk about all of that in another video. But now for this video, you could understand these as virtual particles coming in and out of existence, annihilating each other, and being very spooky. Now, what the inflation theory showed was that if at the start of our universe these particles, such quantum fluctuations did exist in the singularity of Big Bang, you see, such quantum fluctuations would be expanded and made huge because of inflation and the fabric of space and time expanding faster than the speed of light. And such quantum fluctuations would then fall, the gravity of these objects would collapse them into galaxies and into stars. And therefore, the inflationary theory explained how galaxies formed and stars formed and planets formed because of initial quantum fluctuations around black holes. So that is why we know that inflation did exist, because it quite literally solved every single problem that arose because of the Big Bang. Now, moving ahead, you see, just after the inflationary period, 10 to the power minus 12 seconds after the Big Bang, that is still incredibly tiny. 10 to the power minus 12 seconds is 1 by 10 to the power 12. 10 to the power 12 is literally 1 with 12 zeros, and 1 with 12 zeros, 1 by 1 with 12 zeros is 0.0. That is incredibly tiny amount of time just after the Big Bang. You see, what happened is, initially, just before that, our universe was so hot, and the particles in it and everything that existed was so literally hot that nothing could interact with each other. But then, as the universe cooled over time, 10 to the power minus 12 seconds to be exact, you see, energy interacted with itself, and there was the birth of quarks and hadrons. Now, what are quarks and hadrons? You see, we have an atom. In the atom, we have protons, neutrons, and electrons, and these are the subatomic particles. Now, there are three more. What are the smallest particles that humans know of inside protons, electrons, and neutrons, which are quarks. Quarks have 6 flavors, and they are up, down, top, bottom, charm, and strange. And there's a lot of other things about them. That is again another video. But for now, you could understand them as the smallest particles that humans know of. And just this amount of time after the Big Bang, that is incredibly tiny, universe got cooled enough such that quarks and hadrons could form, and now we had the birth of quarks and hadrons, which would of course later go on and make electron, protons, and neutrons, right? Now, you see, after electron, protons, and neutrons were made, after the birth of quarks and hadrons, you see, now we come to that question of why the cosmic microwave background radiation is 380,000 years after the Big Bang, and why can't we look anything before that time period? Now, to understand that, we must first understand what is the Compton scattering. Now you see this scientist right here, he is Arthur Holly Compton. Now Arthur Holly Compton uh, discovered an effect we call the Compton scattering. Now, in quantum scattering, what happens is we have a photon, the particle of light. Now, of course, this hv that is given right here is the formula of the energy of a photon. E equals hv, energy, where E is energy, h is Planck's constant, and v is velocity. That is again another thing. But for now, you could understand that we have a photon, the particle of light. Now, when this light comes and hits a free electron right here, the electron gets recoiled and now it's ionized and it has energy, and the photon gets scattered into another direction from its intended direction. Now you see, just after the formation of electron, protons and neutrons, you see, universe was not cool enough that these electron, protons and neutrons would now form atoms. That is why we had free electrons moving everywhere. Therefore, any light that would be emitted before 380,000 years after the Big Bang, that light would be scattered. And that is why in our modern times we cannot observe the light before 380,000 years after the Big Bang. But what happened after 380,000 years after the Big Bang? We had the recombination era. And recombination era, what happened was these electron, protons and neutrons, the universe got big enough and cool enough that these electron, protons and neutrons could finally interact and form stable atoms. And these atoms were the first elements. They were hydrogen, helium, deuterium and beryllium. These were the four first elements of our universe. And now our universe has the formation of atoms. Now, of course, we don't have free electrons, and therefore these photons that would be emitted at that time will now not be scattered, and therefore these photons can now move freely. And now 13.7 billion years after, scientists did discover the light back then, and this is why the cosmic microwave background radiation is 380,000 years after the Big Bang and not before that, because before that the photons would get scattered. So before that our universe was in a state we called opaque state, because nothing could be really seen with precision, because the light coming from them would be scattered here and there. You could imagine the universe at that time as like a foggy room where nothing can be seen very perfectly. But 380,000 years after, the fog decided to settle down, and now I can see the objects inside that room. So this cosmic microwave background radiation, by the way, was initially discovered by Arno Penzias and Robert Wilson, and they even got a Nobel Prize for that in the 1960s, I believe. Now, moving ahead from the recombination era, you see our universe wasn't really very bright right now. The universe entered what we call the dark ages. You see, now that the atoms and elements are formed, we had a lot of neutral, hydrogen neutral, everything that was neutral, right? Now, the thing is that there was not a light source for there to be for the universe to be very bright. You could understand this as like, let's go to our room again. You see, initially the room was very foggy. The fog settled now that we can see everything, but there is the light bulb in the room has not been switched on. Therefore, there is not a lot of light in our room, and that is why our room is not very bright. Therefore, our room is dark, but it does not have that initial fog that existed. So, these were the dark ages. Now, what happened is, in this time, there was everything was neutral, and things could not interact enough such that they form stars and galaxies. And that is why things were not so bright at that time. But what happened is that after 400 million to 1 billion years after the Big Bang, you see what happened is there was what we call the reionization era. To understand this era, we must understand dark matter halo. Now, picture this. You see, we have galaxies existing, right? Now, scientists found an incredible thing, that for these galaxies to exist in a stable position and in a stable state, there has to be something with its mass and something with its gravitational influence that is balancing, that is stabilizing these galaxies. Now, and so if we took the mass of galaxy that is visible, the mass of galaxies that we see, if that is the only thing that existed, these galaxies would simply collapse, because the mass that exists in the galaxies that we observe is not enough to make that galaxy stable. Therefore, there has to be something that has a gravitational influence, but it does not interact with light, and therefore it is not visible. And that essentially is called dark matter. Now, dark matter, there is the leading theory for what dark matter is what we call WIMP, that is weakly interacting massive particles. So what these are particles, huge particles with a huge gravitational influence, but they do not interact with light, and therefore they are not visible to us, and that is why they are dark, yet they are matter. So dark matter, so there's a dark matter halo around every galaxy, and this is, you could imagine this as the well in our universe, in which all the matter falls because of the gravity and makes galaxies and stars. So this is the dark matter halo. Now the thing is that before this time period, our universe wasn't big enough for these dark matter halos to be big enough to get matter inside them. But after this time period, you see, this dark matter halo got big enough such that the matter around it falls in and makes stars and galaxies. Now, when these stars were formed, you see, these stars release what we call ultraviolet radiation. Of course, we know ultraviolet radiation. What ultraviolet radiation did was that ultraviolet radiation threw that electron out of its orbit from a stable neutral hydrogen, and therefore, when we did not have such stars being formed, because the dark matter halo wasn't big enough to get the stars being formed, the hydrogen was neutral. But after this, there are stars, and by the way, these stars were the first stars in our universe, which were called the population 3 stars. And after these stars were formed, they released ultraviolet radiation, which again ionized these neutral hydrogen atoms, and that is why we call this the re-ionization era. Now, this was the re-ionization era, after which our universe became bright, absolutely bright. So coming back to our analogy, we had our room, the foggy room, the fog settles down, but the room is dark. But now after this re-ionization era, we switch on the light bulb and the room is bright again. So, and by the way, so this was the re-ionization era. Now, one very interesting thing is that in our current universe, 20% of the entire universe is quite literally this dark matter. And this dark matter, something that quite literally nobody knows what it truly is, occupies 27% of the universe. And we know that because if this 27% did not exist, many of the galaxies would quite literally just collapse because they don't have enough gravity for them to be stable. And the normal matter that we see around us, like these books and these stars and everything that makes us, and the 118 elements that exist in the periodic table, all of them that are normal matter are only 5% of our universe. So that is pretty spooky, right? And 68% of our universe is what we call dark energy. Now, dark energy is also called cosmological constant, and what it does is that it is the reason why our universe is expanding. And fun fact, the expansion of our universe, it's accelerating, means the rate of expansion is increasing with time. So our universe is expanding faster and faster and faster with time, and it's accelerating. And scientists, and for there to be acceleration, of course there has to be a force applying on it, and that force is by dark energy. This is, and dark energy forms 68% of the universe, and again we know that because of the rate of expansion of our universe, which is accelerating. So 95% of our universe is quite literally something that we don't know shit about, and only 5% is what we truly see and we imagine and we believed in. That is the normal ordinary matter that we see. So that is pretty spooky, right? Now, and by the way, this is the photo of, not the real photo, but this is population 3 stars, the initial stars which formed in our universe. Now, after this, we entered the most beautiful era of our universe, the stellar era, from 1 billion years to 100 trillion years. That is a huge time interval, by the way. And currently we are quite literally at the start of this era, which we are 13.7 billion years in, and we have to go to 100 trillion years. And And stellar era, of course, is the current universe that exists. After a roller coaster ride of initial plasma, of quantum effects dominating, of forces being unified, of dark ages, of recombination era, of reionization, and first stars, first galaxies, and dark matter halos, and our universe coming from nothing to everything that exists in our surroundings now. And this is the stellar era that we all know and love, with its galaxies, stars, and black holes, and nebulas, and planets. Now, after the stellar era, we now talk about the fate of our universe, the way our universe will die. As we know, every good things come to an end, right? Now, you see, to understand this, the fate of our universe, scientists actually have quite a good idea of the fate of our universe. To understand everything, first we have to understand this thing right here. You see, we have two things: lambda and omega. Lambda is literally cosmological constant and dark energy, the constant in our universe that is making it accelerate. Then omega is the total density parameter, or the average density of our universe, which will determine the gravitational pull of our universe that is going against the dark energy repulsive force, which you could imagine as anti-gravity. Now, so you could imagine these two as anti-gravity and gravity, and their proportion would determine the fate of our universe. So if omega is greater than 1, means our universe is very dense. Eventually, the gravitational force of these of this universe would overcome the dark energy force which is making it expand, and in that case our universe will go all the way back to that initial singularity that we call the big crunch, and maybe after that there is another big bang and we have cyclic universes. Now, all of these are described by the Friedman diagrams. These were discovered by Alexander Friedman, this gentleman right here. And so you see in these diagrams, you can see, so this is the radius of the universe, and we see that if omega is less than 1, our universe's radius will, right now it's increasing. We are about here right now. And after some time, if omega is greater than 1, our universe will start the radius of a universe will start closing, and it will go back to a singularity that started, and this will be the big crunch, and after which we can have cyclic universes and such loops repeating. Now, the thing is, if omega is equal to 1, which means our universe's average density parameter is about this in the same parameter as lambda, that is the cosmological constant, you see our universe will keep on expanding as it is right now, but eventually its expansion will slow down with time. Now, if omega is less than 1, our universe will exponentially expand. So it will expand so crazily because the density is so less that our universe will expand exponentially. Now, this actually depends on the curvature of our universe, the way the fabric of space and time itself is curved or made. If the fabric of space and time has this positive curvature, which is, and by the way, to understand this, we must first understand these three things. So here we have three things. First of all, we have elliptical geometry or spherical geometry, where it would be a spherical type of space with a positive curvature, as they call it. And if I draw a triangle in that, I would have the sum of the three angles of this triangle greater than 180 degree. If our universe follows a hyperbolic geometry, the curvature will be negative. Now, negative curvature means the sum of the angles of the triangle of the universe, if you draw a triangle in the universe, would be less than 180 degrees. And Euclidean geometry, also known as the flat geometry, in this geometry, if you draw a triangle, the sum of its three angles will equal to 180 degree. Now, if our universe has positive curvature, omega will be greater than 1, means our universe's average density will be more than that it will cause the big crunch, which will lead to a closed universe later. Then if our universe is saddle shaped and it has a negative curvature, then the omega or the average density parameter would be less than 1, means our universe will exponentially expand after some time. This would lead to theories like big tear or big rip, which means the fabric of space and time, because of this exponential expansion, would literally tear apart and nothing would be able to interact with anything ever again, because quite literally the fabric of space and time has been torn apart and the laws of physics would break down in that case. Then we have the Euclidean geometry, and if our space is flat, which means omega is equal to 1, our universe will keep expanding, eventually getting slower and slower as it approaches absolute zero temperature. Now, as per current observations, our universe seems to be mostly flat, because scientists draw huge triangles in space and try to measure the flatness or the curvature of the universe, and it seems to be equal to 1, which means our universe is roughly flat. And what that means is our universe will die in what we call a heat death. In heat death, what we will have is, that is the most probable fate of our universe, in which our universe will keep expanding, and as it's expanding, its entropy will keep reaching a lower, will keep increasing. Now, what does entropy mean? You see, entropy means the amount of disorder in state, or the ability for it to spread. And laws of thermodynamics, which are again another topic for another video, but in this video, to come to for understanding the fate of a universe, you see, entropy's law says that everything likes to go from a highly usable energy state to a lower usable energy state, or lesser usable energy state. What that means is, if I have petrol is highly usable energy state because it has a lot of stored chemical energy that I can use to run a bike or a car. Now, once I burn this, you see, it spreads, and now it's in gas form, which is less usable than its petrol form. So everything likes to go from a highly usable energy state to less usable energy state. Thus, the entropy of our universe keeps increasing. Now, you see, this is actually related to the arrow of time itself. Why the arrow of time is forward in time. We'll discuss this in another video. It's also very interesting. Now, the thing is, our universe is entropy is increasing. Now, since it's expanding continuously, and as it's getting slower and slower, its entropy will keep increasing and making it less usable, and it will reach the absolute zero temperature, which is the 460 degrees Fahrenheit, or minus 273.13 degrees Celsius, which is the temperature at which entropy will literally be maximum, such that nothing in our universe can interact, and there is no usable energy left in our universe. So if our universe does go from heat death, then our universe will reach a point after trillions and trillions of hundreds and thousands and trillions of years, after which our universe will reach a time when there is no usable energy left, and everything will be quiet and dead. So that is the most probable fate of our universe. But of course, the other possibilities are also possible. Now, with this, we come to the conclusion. I've drawn a chart here. You could look at this chart. You could take a screenshot. This has all the eras of our universe, starting from the Big Bang, going to the Planck era, where physics breaks down. Then the fundamental forces unified, and there was the grand unification era, as they call it. Then there was quark formation, hadrons formation, then protons and neutrons being formed. Then, of course, electrons and neutrinos dominating. Then, of course, the photons being scattered everywhere. And 380,000 years after, we are having the recombination era and CMB being released. Then the dark ages. Then, once our universe is big enough, there are stars and galaxies being formed, and the neutral hydrogen being reionized again, and making the universe bright again. Then the modern era that we love and live in, stellar era, after which stars die and only white dwarfs and neutron stars will live, along with black holes, which is the degenerate era. And then finally, after only black holes are left and literally everything dies, we have the black hole era, which is 10 to the power 40 years afterwards, which is crazy to imagine. And even black holes aren't eternal. They will evaporate via Hawking radiation. I've talked about Hawking radiation in my quantum mechanics video. You can go check it out if you want to. Then we finally have the heat death after crazy time. And usable energy remains. And everything is cold, dark, and dead forever. But of course, there is other possibilities. That everything goes back and comes into one singularity. And then we have a big crunch. And then cyclic universes, and quite possibly everything happening literally the same way again and again in a cyclic form. So that would be absolutely crazy, of course. But the most probable situation right now is the heat death of our universe. You can take the screenshot of this. Now, after this, to end this video. By the way, sorry for that turbulence in between. That was just a misclick. Now, I want to also at the end give one perspective of mine about the existence of very Big Bang. Now, to me, the very existence of Big Bang and the initial conditions of Big Bang existing prove that there has to be something, a higher consciousness that created that very information and energy that made the singularity of Big Bang. And the reason why I say that is because in my other quantum mechanics video, sorry for the hiccups. In my other quantum mechanics video, I've talked about of our consciousness, of human consciousness, not truly being so conscious as I would like to define it. I've talked more about higher consciousness, determinism, free will, etc. in my other video. You can check it out. Now, the thing is, at the end of this video, I just want to tell you that if there was the existence of Big Bang and the initial energy and the initial conditions of Big Bang, there has to be, in my opinion, something, a higher consciousness that could create information and energy that would create the Big Bang. I just don't think that the very existence of existence or even the existence of non-existence or quite literally anything just possibly having an existence or a form requires some initial thing that created it, and I just cannot see how everything can exist in a form without an original creator. Even if nothing existed, quite literally the existence of an atom or even the existence of a quark would prove to me the existence of a higher consciousness that has created it. Now, that is why I'm leaned to believe towards the fact, not the fact, but I'm leaned to believe that there has to be a creator, an author of the universe that created everything that we have seen or imagined. That is the Big Bang. Now, of course, I've talked more about all these topics in my other video. You see, I've talked about higher consciousness, determinism, free will, and quite literally the very essence of reality and our existence in my quantum mechanics video. You can go check it out. It's very fun, you would love to imagine it, and it will such concepts, quantum mechanics, the age of universe, and many other things that we are going to discuss on this channel. Many other mind-boggling concepts. So it will be a fun journey. Last video, the editing wasn't pretty good, and of course the quality wasn't either. This time I figured out a better way. I'm learning along with this, so this time I hope the video is better. And now I hope all of you subscribe, like, and the things, and please support, because I think such concepts are really intriguing and very awesome, and something that really give you another perspective for life. And makes you really enjoy life in a sense. So now with this, we come to the end of our video. I hope all of you enjoyed talking about the very existence of the current universe, the very start of it to the very end of it, and beyond our universe. With this, we'll come to the end of this video. We'll make further videos, so stay tuned in for other ones. And I hope you keep enjoying my videos. Thank you so much for watching. And with this, yeah, thank you.